Welcome to the first day of Summer General Physics Video 4. In this video we'll be looking at units, their importance in physics, and then also how you can perform unit conversions and do something called dimensional analysis. So in physics, units are very important because we'll be dealing with a lot of physical quantities, things like volume, distance, speed, that all need to be expressed in units. After all, if you have 300 grams of M&Ms, that's way different from having 300 kilograms of M&Ms. So whenever we write down a quantity, we want to include units. And it's very important when you do quizzes and exams that all of your quantities are expressed along with units. Now, all units can be expressed in terms of fundamental units, and these are things like length, time, Kelvin temperatures, moles, and meters. And so, for example, an area is a length squared, or a square meter in the SI system, and speed would be length divided by time. Think meters per second or miles per hour. Now, on May 20th of 2019, which was actually during one of the summer physics sessions previously, the SI system was revamped, and we have new definitions of some of these fundamental SI units. This is because there was a problem before that some of the fundamental SI units were based on things like a lump of metal in a vacuum jar in France. And if you have a lump of metal, well, an atom could fall off of it, and then your very definition of a kilogram would change. And these definitions weren't precise enough for the very sophisticated measurements that scientists are capable of making these days. And so all of the fundamental units were tied to constants of nature, things like the speed of light. And because they're now tied to constants of nature, as instrumentation gets better and people are able to measure things more precisely, then we don't have to worry about our fundamental units being imprecise. So this doesn't really affect us, this change in the SI system doesn't affect the calculations we'll be doing in general physics, because we won't be carrying out measurements of very, very high precision. But it's just kind of neat to know that the system was changed and that all of the constants of nature are now used to define these units. Now, as we mentioned before, in physics we are describing everything from atoms and particles to galaxies. And so we need to express very wide ranges of numbers. And one of the things that helps us to do this are unit prefixes. And you can see here a table of unit prefixes. And the way that these prefixes work is that when you add them to a measurement, then they imply multiplication by a power of 10. So for example, a centimeter, if we look on the table, we see centi means 10 to the minus 2, so 1 centimeter would be 1 times 10 to the minus 2 meters, or 0.01 meters. On the other hand, 3 kilometers is 3 times 10 to the third meters, or 3,000 meters. Now, one question I always get asked during class is, do we have to memorize this whole table of unit prefixes? And the answer is no, you don't. The most important ones are centi, milli, and kilo. So you should know how many centimeters are in a meter, you should know how many millimeters are in a meter, and you should know how many meters are in a kilometer. So you should be able to go between centi, milli, and kilo. Those are the ones you should memorize. The other ones on this table, if they pop up in an exam or quiz situation, I will give you their definitions. Another thing we need to be able to do with units is to convert them from one form to another. So let's take an example. Let's say you can pour a glass of milk in 5 seconds, so you know your pour rate is 1 glass in 5 seconds. So 1 glass in 5 seconds, which is equivalent to 0.2 glasses per second. And you want to be able to convert this to cubic centimeters per minute. So here we have a volume, a glass per second, so that's time. And here this is a different volume per time that we want to convert this number to. So how would we do that? So as you may have learned in other classes, what we need to do is multiply this 0.2 by some conversion facts. And maybe I don't know how many cubic centimeters are in a glass, but I know some intermediate facts that I can use to help me along the way. The important thing is when you are arranging these conversion facts, you arrange them so that the unit that you don't want, in this case glasses, gets arranged so one is in the numerator, one is in the denominator so that they can cancel, and then that would leave you with cups. So to change this volume measurement from glasses to cubic centimeters, one fact that I know is that a glass is 2 cups. So I'll arrange it like this so glasses cancels with glasses. And then I also know that there are 16 cups in 1 gallon. So once again, cups would cancel with cups. And another conversion fact that I can look up is that 1 gallon is equivalent to 231 cubic inches. So here, once again, gallons can cancel with gallons. And then another fact is that an inch, 1 inch, is equivalent to 2.54 centimeters. And here I need to cube things because I have cubic inches here, so that needs to cancel with cubic inches down here. And then the centimeters can also get cubed so that my final answer can be in cubic centimeters. So now that I've changed glasses to cubic centimeters, I also need to convert seconds to minutes. So seconds is in the denominator of my original quantity, and so I need a conversion fact that will go between seconds and minutes. So 60 seconds is equivalent to 1 minute, and seconds can now cancel with seconds, and I'm left with cubic centimeters per minute. So when I do this conversion, what I'll do is I'll take the 0.2, multiply it by 2, so 0.2 times 2 divided by 16 times 231 times 2.54 cubed. I have to be careful and remember that the cubed doesn't just cube the centimeters and the inches, but also cubes the numbers as well. 1 cubed is still 1, but I have to multiply by 2.54 cubed. Then I multiply by 60, and the final result is 5.7 times 10 to the third cubic centimeters per minute. So here's a question that you can look at. Let's say you know that a camel can drink 20 gallons of water at a time. Let's say you have 600 liters of water and you wish to store your water in camels. How many camels would you need to drink this much water? And as an intermediate conversion fact, I know that 1 gallon is equivalent to 3.786 liters. So give this a try and pause the video, and once you have an answer, see if it's close to any of these numbers. Okay, so now if you have your answer, let's take a look at going through this together. So I think I'll need a bit more room to write. So I will pop over to my writing pad and see if we can do this problem together. So the first thing I want to write down is the quantity that I know that I have. And in this case, I have 600 liters of water that I want to store in camels. So I start with my 600 liters of water, and I need to convert this to camels. Well, I don't know the direct conversion between liters and camels, but I have this intermediate fact that 1 gallon is equal to 3.786 liters, and I know how to relate gallons to camels. So first we'll convert from liters into gallons. So I will need to write my conversion fact down so that liters is in the denominator, so it can cancel with the liters here. So I have 3.786 liters, and that's equivalent to 1 gallon. Then I have an additional fact that will allow me to go from gallons into camels. So I have 20 gallons that will fit inside 1 camel. So if I do that multiplication, if I take 600 liters divide it by 3.786, and then divide that by 20, I find I get 7.92 camels. So 7.92 camels would be the response I would want to select. Of course, in this case, in reality, we would probably want to have 8 camels because camels tend to be rather integer quantities. And now at this point, someone usually asks me, do I need to memorize the conversion factor between gallons and liters? And no, if we are using any English units, any non-SI units, that we need to convert between those and SI units, I will give you those conversion factors. So the last thing we want to talk about in this video is dimensional analysis. And dimensional analysis is all about having units that agree when you do mathematical operations with them. So for example, in this sign here, we have a sign that claims that in New Koyama, there are 562 people. The town is 2,150 feet above sea level, and it was established in 1951. You add those numbers together and you get 4,663. What does this number mean? It means absolutely nothing, because these numbers all have different units, they're all very different kinds of things, and adding them together just doesn't make any sense. And this is what dimensional analysis is all about. It's handy for equation checking and allows us to see if an equation makes sense. So if you have an equation, the units on one side of the equation should match the units on the other side of the equation. In addition, if you have multiple terms that are added together, those terms should have the same units. So you can plug in what the units are for different variables and then check to make sure that the units do in fact match. So if we use this equation as an example, we have a distance, which is a length, is equal to 1/2 acceleration, which happens to be a length over a time squared. We'll learn more about that later, times time squared. So the time squareds would cancel, and we have length on one side and length on the other side of the equation. Now over here, we have an equation that suggests that distance is equal to velocity over time. Distance has units of length. Velocity has units of length over time, like miles per hour, and time has units of time. And so if we simplify this equation, we get length over time squared, and that's equal to length. No, the units don't seem to match at all. And so this equation is definitely incorrect. Now, over here, the dimensional analysis checked out, but we didn't use the fact that there was this 1/2. So dimensional analysis can tell us if an equation is definitely wrong, but it can't necessarily tell us that an equation is correct because it doesn't give us a way for checking these constant factors. So let's try that out. We want to know which of the following could possibly be correct. So in equation A, we have velocity is equal to an initial velocity. That's what the sub-zero means, that this is an initial velocity, plus an acceleration times time squared. Here we have a volume is equal to an area times a height, and the last equation says that a mass times an acceleration is equal to velocity squared. Which one of these could be correct? And I have, as a hint, I have the SI units for all of these various quantities. So go ahead and do some dimensional analysis on these three equations, pause the video, and figure out which one of these equations could be correct. Okay, so if you have your answer, let's take a look at these different equations. So first we'll take a look at the first equation, equation A. And equation A suggests that velocity is equal to an initial velocity plus an acceleration times time squared. And we can fill in the units for each of these quantities. A velocity is meters per second in SI units. That's going to be equal to meters per second, since this is just an initial velocity, plus acceleration has units of meters over seconds squared, and then time would be seconds, but that gets squared. And so we see in this last term, we have a second squared over a second squared. Those cancel. So what we're trying to do is add a distance to some velocity. So here we have velocity, here we have velocity, but we're adding a velocity to a distance. That doesn't really make sense. These units don't match. You need not only the same unit on both sides of the equation, but if you're adding multiple things together, each thing needs to have the same units. So this one, that's not going to work. That can't be correct. What about B, which insists that we have a volume here. So here, this is a different V. Instead of a little v meaning velocity, this is a big V meaning volume, is equal to area times height. So volume has a unit, or its units are meters cubed. This is going to be equal to area has units of meters squared times height has units of meters. So if we combine the two terms on the right-hand side, meters squared times meters is meters cubed. So we do have the same units on both sides of this equation. So this could potentially be a correct equation. Now, just for the sake of completeness, let's look at C. So for C, I have a mass times an acceleration, and I'm suggesting that that's equal to velocity squared. So mass has units of kilograms, acceleration has units of meters over seconds squared, and that's going to be equal to velocity squared, so that's meters over seconds, and both of those get squared. So if I look at this third equation, boy, the units don't match at all. Here I have a meter squared, here I have a plain old meters, there's a kilogram on one side but not the other. This isn't going to work either. So of these three equations, the only one that works is B. So that would be the answer that I would select. So that's the end of the video on units. Then in the next video, we'll be looking at significant digits and then also estimation.